Hello, welcome to the lecture on atomic spectra. So, atomic spectra, it is nothing but the spectra of electromagnetic radiation emitted or absorbed by an electron uh, during its transition between different energy levels within the atom. So, we have a nucleus which has protons and neutrons, and then we have different energy levels like this. So we are going to give the different energy level and identify it with principal quantum number. So starting from here, n is equal to 1, n is equal to 2, n is equal to 3, and so on. So here the orbit which is closer to the nucleus has more energy. So n equal to 1 orbit has more energy, then n equal to 2, and the energy keeps on decreasing in this fashion. So now we know that electrons exist in these orbits. So whenever, for example, there is an electron here, whenever the electron moves to from higher orbit to lower orbit, that is high energy orbit to low energy orbit, so it will emit the photon. That is, energy is emitted in the form of a photon. And whenever electron, suppose in n equal to 3 we have an electron, and if this electron absorbs energy, then if suppose it absorbs a sufficient energy to come to n equal to 2, then it is absorption. So it is emission of energy or absorption of energy by electron during its transition between different energy levels, so within the atom. That is uh, that is described as atomic spectra. That is a phenomenon of atomic spectra. So the spectrum of light emitted by an element, it is the characteristic of that element. For example, we have different elements like say boron or beryllium or carbon. So thus, based on the spectrum that we get, electromagnetic spectrum, we can identify the characteristic of the element. So essentially, that spectrum forms the characteristic that determines the element. So each element has orbits around it. So and different energies. Each atom has different energies of orbits. So the transitions will give the emission spectra or absorption spectra that will help us to identify the elements. So that is atomic spectroscopy, which would be seen later. So we have sodium lamp. So the sodium lamp will emit yellow. It emits photons of wavelength 589 nanometer. So this is the wavelength of photons of light emitted by the sodium lamp. So this is the characteristic of the sodium element. So this will be yellow color light. So the characteristic spectrum of atoms, it is composed of discrete lines that are the fingerprint of the elements. In in 1880, a physicist known as Fraunhofer, what he did is he used spectrograph and he measured the wavelength of lines from the sunlight, and by analyzing those lines from the sunlight, he detected the existence of helium atom. And So not only the atoms but molecules also will have the characteristic spectra of emission or absorption. And in the case of molecules, we will identify closely spaced lines. Unlike atoms, where we get discrete lines, here we get the lines which are closely spaced. And for some large molecules, we even get continuous spectra. So um, this is how the spectra of molecules is different from uh, atomic spectra, where in the case of molecules we will get closely the lines of spectra are closely spaced, that is, and or in case of large molecules even the spectra is continuous. And in 1888, a Swedish physicist named Rydberg, so he had found a mathematical formula for the spectral lines of hydrogen. So in that, his Rydberg formula is like 1 by lambda. This is the wavelength of emitted photons. This is only related to he found for hydrogen spectral lines, and this is equal to R, which is Rydberg constant, by 1 by nf square minus 1 by n I square. So in this you can see that nf and ni are two different energy levels. So suppose if the electron is transiting from n equal to 1 to 2, this 2 is nothing but nf, that is final orbit, and n equal to 1 is initial orbit. And suppose if the electron comes from n equal to 3 to n equal to 2, then nf will be 2 and ni will be 3 here in this case. So this is actually for emission, he has given the formula of hydrogen atom. So lambda is wavelength of emitted photons, and R is Rydberg constant. So, so what I am doing is I am mentioning uh, the orbits as straight lines just to express the transitions here. So these are different energy levels, basically identified with principal quantum number. And so, and mind that this spacing is not uniform, it will be non-uniform, but just for representing transitions, I am drawing these lines. Okay, there could be lot many, but I'm just for understanding, I'm drawing few lines here. I'm naming these energy levels as n equal to 1, n is equal to 2, n is equal to 3, n is equal to 4, 5, 6, and 7. So n equal to 1 has higher energy, and the energy goes on decreasing as the n increases. So all the transition between n equal to 2 and the other orbits, then that is called a Balmer series, like between these two or these two. So all these transitions are called Balmer series. So this is nothing but Balmer series. And now transition between n equal to 1. This is called Lyman series. So it will be like in here. These are the transitions. Obviously, even from higher also, and it is Lyman series. Similarly, between n equal to 3 and higher orbit. So this is about emission. This is all about emission because this is from lower to higher is sorry higher to lower is involved. And see here for Brahma series we are not mentioning the transition between n equal to 1 and n equal to 2. Here n equal to 1 is higher energy. So here that transition is not mentioned. That means this is a emission one. And here also it is emission one anyway because n equal to 1 is the highest one. When the electron moves from higher to lower orbits, lower energy orbits, uh, energy will be emitted in the form of photons. And same goes with Paschen series. Here, the transition between n equal to 3 and lower energy orbits like this. So this is Paschen series. And here, in each of the series, the first transition is called. So here it is the first line, like so. This is called Balmer alpha line. As we, it is about hydrogen. This is also called H alpha line, and the wavelength of photons emitted by this transition, that is from n equal to 2 to n equal to 3, that will be the wavelength will be 656 nanometer. This comes under red color. It falls in red color. And whereas this transition, so here we can see that when the electron moves from n equal to 2 to n equal to 4, there will be more energy released. When the energy is more, the wavelength will be less, and that is called Balmer beta line or H beta line with wavelength lambda is equal to 486 nanometer, and this is blue color, blue light or blue photons. And so, how about in this case, n equal to 2 to n equal to 5, and the energy will be even much higher, and that falls in UV region. So, all these transitions will come under UV region or even higher energies. So, UV and so on, based on the amount of energy emitted during this transition. So, the energy of the emitted photon will be is equal to the energy difference between these levels. So for example, for this transition, the difference of energy between n equal to 2 and n is equal to 5, that will be the energy of the photon emitted with that particular transition. Now for further analysis, let's use another quantity called wave number. So wave number, it is noted by, and its units are either meter inverse or centimeter inverse, and the wave number is equal to 1 by lambda. So lambda has units meter or centimeter, so wave number units will be meter inverse or centimeter inverse. So now we will see the relation between these lines. So these lines or these different transitions, that is we can establish the relation between different transitions using a formula like so so here wave number is nothing but it is a quantity of a photon, emitted photon. So we are considering three photons, for example. We will see how these are related. So three photons. So each photon represent different transition here. So now this quantity, this wave number, it represents transit. It is a second line of Balmer series. So how the transition would be? In this case, NF will be 4 and Ni will be 2. As you can see here, this is the second line, as I mentioned. This is n equal to 4 and n equal to Ni is 2 here. So from second to 4 it is moving. And now let's see what is the wave, what is the photon presented by this wave number one. And so it is nothing but first line of Paschen series. So here Paschen series is this, in which n is equal to 4 and n equal to 3. So here NF is nothing but this is the first line of Paschen series. So this is the first line of Paschen series, this arrow, particular arrow. So here n equal to 4 and n equal to 3. So NF is 4 and Ni is 3. And so how about this one? So it is first line of the Balmer series. So first line of Balmer series is this, in which n is 3 and n. So here NF is 3 and Ni is. Okay, and so this is the first line of Balmer series. So you can see here that NF is 4 and Ni is 2, and it is 4, 3, 3, 2. So here uh, this new wave number 2 plus wave number 1 we are adding. From this relation you can see. So this establishes the uh, energy relation. Like, so here we know that uh, energy E is equal to h nu, and nu is nothing but c by lambda, and 1 by lambda is this new broad, like the wave number we are representing. So h is c. So here h and c are constant, and this wave number is not constant. That is, energy is directly proportional to the wave number. So the difference of these energy levels is the sum of the difference in energy level between these two and these two. So that's why, as energy is directly proportional to wave number, we are able to write in this fashion. So this is the relation between different lines uh, in the spectrum. And from Rydberg formula, we can identify that energy is inversely proportional to n square, where n is the principal quantum number, so that we can identify. And when we look at these uh, transitions, so here we have seen that we get photons in of red color, of red or blue color, so on. And in case of the Lyman series, we get photons that fall in the UV region, and the and the other transitions, like in Paschen series, the photons having wavelength greater than the Balmer series one, uh, those will be in the infrared region, and those can be identified using a photographic film. So they hit the photographic film, and the those infrared region photons will be identified by the photographic film. So based on the transitions, we have three different kinds of spectra. Like one is emission spectra. This happens when electron moves from high energy orbit to lower energy orbit or level. In that case, energy is emitted, and the energy is emitted in the form of photons. That is emission spectra. And the next is absorption spectra. And in this case, the electron moves from lower energy orbit to higher energy orbit by absorbing energy. The energy is absorbed is light energy, that is photons are absorbed of the equal amount of energy. And the next one is the continuous. Whereas continuous spectrum has no breaks, so that will be formed as a band. And the study of these spectra, that is the spectra of electromagnetic radiation absorbed or emitted by an electron, this is known as atomic spectroscopy. So, atomic spectroscopy, it is used for identifying the spectral lines of materials used in the metallurgy. So, used to identify materials used in metallurgy. And we have different types of spectroscopy. One is uh, emission atomic spectroscopy, absorption atomic spectroscopy, and fluorescence atomic spectroscopy. So, atomic emission spectroscopy, atomic absorption spectroscopy, and atomic fluorescence spectroscopy. So, this is the application of this phenomenon. So, in this lecture, we have seen what is atomic spectra, and we have seen Balmer, Lyman, and Paschen series of how how they are formed based on the transition of electron between different energy levels. And we have also seen what is wave number and how it is corresponded to energy, and how we can relate different lines uh, of the spectra. And and we have also seen how the phenomenon of this atomic spectra is used full far. So this is the end of this lecture. Please subscribe the channel to get more videos related to physics and nanotechnology. Thank you for watching. We'll see you in the next lecture.